Hello everybody, welcome back to a new week here in continuous learning, remote learning, online learning, distance learning, learning without walls, whatever you're going to call it. Hope you're hanging in there. As you can see, we teachers are getting a little goofy, but par for the course. I'm actually filming these videos ahead of time so that I can help you guys through the math. And I just want you to see what I'm seeing out my window. It's freaking snowing. April 17th, it's snowing. Okay, so why not do a little trig? That's what I thought too. Okay, bringing it back. Today we are going to continue our use of the unit circle, and we're going to make it much more algebraic and much cooler, I think. And we are actually going to unfold the unit circle and create what we are going to call trig functions. This video is going to probably be a tad longer than 30 minutes. However, I know we're trying to keep our instruction around 1 hour, so this one might run a tad longer, but your next video this week will be shorter. This is kind of the big thing, and then I'll show you a couple uses next time. So bear with me, this is your big learning for the week. Something I would definitely have handy if I were you, just to help you with your practice problems, and as we move into the next lesson, is I would have a couple sticky notes. 3 to be exact. This is what I typically do in order to take just the important information out of here. So as we move forward here, we are going to go back to our unit circle. So the key points that I'm going to start with, I'm mainly going to work within the first quadrant here. And let's just get our points down. So if we are continuing, or if we are going to consider a radius of 1, hence the unit circle, this first point here at 0 degrees, 0 radians, is going to be 1, 0. As I travel up, here we are at 90 degrees, or pi over 2. And we know that this point here is going to be 0, 1. And we can keep going all the way around, and we will, you know, eventually. But for now, I'm just going to focus on this first quadrant. As you all know, I like to then create my next, I like to take half of that because I'm going to be lazy and I'm not going to use a protractor. That doesn't even look like half, but it's going to count. So this right here is going to be our 45, or half of half is going to be pi over 4. And as we now know, or are getting to know, this point right here is going to be root 2 over 2, root 2 over 2. In terms of our horizontal distance and our vertical distance traveled. If I go for our smallest piece of pi that we typically study on the unit circle, we're just going to eyeball it and call that my 30, or my pi over 6. My don't even waste your time slice of pi. And this travels all the way over root 3 over 2. And then just up a short distance, which is my 1/2. And then I'm running out of colors here. We're going to use a blue, but that's probably going to show up like black. So there we go. This last one is going to be my 60, my pi over 3, or my short distance, long distance, which will be 1/2 root 3 over 2. Okay, so as you know from the unit circle from last week, we are going to continue this pattern all the way around to my various quadrants. So we're going to end up with negative, positive, negative, negative, and then positive, negative in the fourth quadrant. Okay, so from last week, we discussed, our last lesson, how cosine of an angle is going to refer to the x values, or the horizontal distance traveled. So my cosine values are going to be all of my x values, and here's where I'm going to start. So if I were to take these values and what we call unfold the unit circle, I could create a cosine function. So what I'm going to now do is I am going to be mapping for every input of an angle. My output value is going to be my x value, because we are going to be graphing the cosine function. So I'm going to start with a function whose input is an angle measure, theta, and whose output is the cosine value at that angle. So here's the first one that I'm going to try to create a function for. All right. So once again, notice the input is going to be my angle measurement, and my output is going to be the x value of the unit circle. All right, so let's see what that looks like. If my inputs are my thetas and my outputs are my x values, the greatest x value that we need is going to be, or the greatest output value that we need is going to be 1. The smallest output value that we're going to need as we travel around the unit circle is going to be -1. So our outputs aren't going to take up very much room. I'm probably just going to extend them a little bit here. So here are my output values, f of theta. My input values, remember I want to go up to 1 and down to -1. So my input values are going to be all of those theta measurements. Now notice we go all the way from 0 degrees all the way to 360. So I'm going to make my horizontal axis quite a bit longer. Okay, so cosine of theta looks a little different. If you guys go onto Plan Book, there is actually a Word document that has this nicely printed out and beautiful, and we do that when we're at school, but we're not, so we're just going to use a piece of paper. It'll look a little messier, but if you're interested, go ahead and print that out if you would like. Okay, so I'm just going to kind of set up my structure a little bit. We talked about my outputs being my cosine values. So I go anywhere from 1, that's my largest x value, and then I get smaller, 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 smaller. Remember, we're mapping x values. So that's going to be all of these distances traveled. And then I'm going to get smaller and smaller and smaller all the way out here to -1. So when I label this, I'm actually going to label largest is 1, smallest is -1. Now they're going to be, as you can see, it's going to be a repeated pattern or a periodic pattern, which is why this works really well for modeling periodic motion, such as waves or sound or light. So what I'm going to do now, after I have this set up, is now I'm going to set up my inputs. So remember, my input values are thetas. My input values are all of my angles as we travel around. So Miss Wheeler taught me this one. I'm going to start with my lowest input value, which is 0. And I'm going to travel all the way out to my greatest input value, which is 360. Now, we can also, of course, do this in radian measurements. So this one is going to be 2 pi. And again, that one's going to stay at 0. All right, well, halfway around the unit circle gets me 180 or pi. Okay, well, what's half of that? 90 or pi over 2. And now what's going to be our third important point is going to be right here at 270 or 3 pi over 2. All right, so here's where I'm going to kind of start. This is going to be my structure for my cosine. It's also going to be the structure for my sine, so it's going to take a little bit longer on this one. All right, so let's see what happens here as we unfold this unit circle. So again, my eyeball is only going to be going to the x values because I am only graphing the cosine values at a certain angle. Okay, well, when my angle is 0, let's go ahead and look at what happens at 0 degrees or 0 radians. My x value, my cosine value, is going to be up here at 1, so I'm going to place my point right there. That is where the cosine exists at an angle measurement. I should probably put angle there. Okay, now let's see. Let's just hit these for now. What about at 90 degrees? At 90 degrees, my cosine value is 0. So rather than being up at 1, my cosine is going to get smaller and smaller and smaller and smaller until I'm here at 0. All right, keep traveling. At 180 or pi, I'm actually going to be down at -1. So this is going to be right about here. At 270 Remember, I'm at 0, -1. At 270, my x value is back here at 0. And then all the way back around at 360, or at 2 pi, I'm going to be back up here at 1. Remember, we're mapping x values. So x values start large. They get smaller and smaller and smaller and smaller and smaller and smaller and smaller. And then they end up getting bigger and bigger and bigger and bigger. Okay, so what's going to happen with this function is it's somehow going to get from 1 to 0 to -1, back to 0, and up to 1. And that's going to be one cycle through the unit circle. Now, it could keep going and going and going and going as you travel, but for now, we're just going to graph kind of the parent function. All right, so let's see what happens in between. Well, all right, let's go in between. I'm going to try to keep my colors consistent. At pi over 4, now notice I'm going to kind of start going into radians here. We usually graph these in terms of radians. So I'm going to go with pi over 4 is going to be this value. Well, half of this is going to be, where am I now? 3 pi over 4, 4 pi over 4. So this one's 5 pi over 4, 6 pi over 4. So this one's going to be 7 pi over 4. Again, good thing you learned that unit circle. Okay, well, halfway between these big values is going to be these 45s, or these fourths. So I'm here at root 2 over 2. Well, what the heck is root 2 over 2? Well, I happen to know that the square root of root 2 over 2 in terms of a decimal is going to be approximately 0.71, and I'm going to stick with that. So I am getting smaller from 1 to about 0.71, blah, 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 blah. So maybe that's going to be about right here. All right. But that means as I go into the second quadrant, that's going to be a negative number. So now here I'm going to be down 0.74. We're just going to get a little messy. Oh, well. And then third quadrant, negative divided by a negative. When I do this cosine value, I'm still negative. I'm not dividing. What am I doing? I'm still negative, so I'm here. And then here I'm going to be back up to that point, or that positive x value. Negative, negative, positive. All right, so we start positive. We hang out of the negatives for a while, and now we're going to go back up positive. You can kind of see what's being created here. Now I'm going to go to my 30s. Root 3 over 2. Okay, wait a second. So root 3 over 2 is definitely going to be larger than root 2 over 2. It's approximately 0.87. So here at my little cute little 30s, which is maybe about right here, I'm going to be up here. And then I'm going to be down here. And then I'm going to be down here. You can tell that this is not going to be a linear change in between. And the very last one that I'm going to do is going to be 1/2. Oh, well, how nice is that? 1/2 is 1/2. So 1/2 is just at 0.5. So I can do that one. Here at my 60s, I'm here at half, which is kind of nice. So here at my 60s, I'm at half, and I'm at half, and I'm again here at half. Okay, so what you can see has occurred is, if I were to connect these dots, I start out at an x value, or an output value of 1, and then I'm going to connect these points, and what you're going to get is this wave. We've created a cosine wave. And now, like I said, this is going to keep on going this way forever and ever and ever, or until I restrict this domain. And then the same thing on this side. But for our purposes, if I'm looking at the parent function for cosine, one trip around that unit circle looks something like that. Now, every time you graph cosine, you are not going to have to graph all of these little components in between, because you're going to understand that this does not change with a linear constant rate of change. It changes slow at first and then quicker as you move towards the 90 degrees, and then quickly at first and then slows down. So you are going to create this curve. Now, I always threaten my students and I say, if I can't see that curvature within your trig functions, I will make you graph every single one of those little points. But so far, no one ever has. So enter sticky note. we have some things to consider. Actually, before the sticky note, we can talk about a couple things with every trig function. So as I look at this parent for cosine, one thing that we can discuss about the parent for our trig functions is something called the period. So when we discuss the period for one trig function, we are talking about the time that it takes for one full wave to unfold. So we're talking about the number of degrees or the number of radians that it's going to take for a full cosine wave to unfold. So in this case, our period is going to take 2 pi in order to travel all around the unit circle. So the parent function, the period, the time that it takes for one to unfold, is going to be 2 pi. That's going to talk about our horizontal distance traveled. So 2 pi, this is going to be our horizontal distance traveled. Another thing we can talk about is we can talk about the amplitude. Now in your science classes, you probably have already discussed amplitude of a wave. And if we were in class right now, you would all be shouting out, oh, that means the height of the wave. Absolutely correct. So the amplitude is going to be our vertical distance, and this is going to be the height of the wave from 0. So when we talk about the height of the wave, we're only talking about how tall is that wave, what's the vertical distance traveled between 0, or the midline, and the uppermost part of the wave. So for this parent function, as the wave is 1 unit in terms of amplitude. And the last thing that we can talk about is we can always talk about the range. Now, the range, of course, is still going to refer to our vertical or our outputs. So our range is going to travel, remember, lowest to highest, so increasing. So we are going to start seeing this function at -1 all the way until +1. And that is going to be inclusive. So my outputs travel inclusively from -1 to 1. So range has not changed. Okay, how come we don't have domain? If we have range, where's the domain? Oh, that's right. Domain is going to be referred to as the period, or how long it takes to unfold. All right, so cosine took us the longest. I see we're at about 17 minutes, my favorite number and yours. So at this point, I want to get a sticky note because there's a lot going on with cosine. And as I move forward, I do not need all of these values. So right now, I'm just going to get a handy dandy little cheat sheet here. And the most important thing that I need to know, besides the fact that I am making a cheat sheet for cosine of theta, is just our parent points. So as we move forward, as you know, in all functions, there's an infinite number of points here. Now, these are our nice, convenient points on the unit circle, but there's millions and billions and quadrillions of points here. We are only going to be concerned with our parent points. So our parent points for cosine are going to, of course, include our 1s. It's going to travel from 1 down to -1. We are going to unfold our parent all the way out to 2 pi, from 0 to 2 pi. And now I'm going to create the big 4. So half of 2 pi is pi. Half of pi is pi over 2. And then, of course, half of a half, or 1 pi over 2, 2 pi over 2, 3 pi over 2. You know, when you find the pattern, you can ignore the fractions. Okay, so my parent points for my vertical dimension are going to be -1 to 1. My horizontal dimension, or my theta values, are from 0 to 2 pi. And now these are going to be my only points that I'm going to continue forward when I graph. So at 0, remember, cosine is the x's, so I start way out there at the unit circle on 1. If you think about the x's, as you travel through, you travel from 1 in my x's to 0 to -1. So I'm going to go from 1 to 0 to -1 and back again. And now here's where you have to create that curve. Otherwise, I'm going to be mean and make you plot all the points in between. Not bad. All right, so there's my cheat sheet. The period for the mama is going to be 2 pi. The amplitude for the mama is 1. And my range is going to be my outputs travel from -1 to 1 inclusively. So here's where we kind of, made it all happen. That's the beautiful stuff. This is the necessary stuff. All right, so I'm just gonna, I don't know, I'm gonna do this, throw this up here. Throw that up there for later. All right, next one we have to do is we need to do sine. So sine's gonna go a little bit quicker because we've kind of already talked through all of this information, but the only thing that's gonna change is that this time we're going to be dealing with our sine values, which means instead of our x values, we're gonna be dealing with our y values. So this is gonna have the next function look a little different. I'm trying to see if I have enough room. I definitely have enough room. So I'm gonna go f of theta is equal to sine theta. Oh my gosh, I love trig functions. I'm so sad that we can't be together to do this. All right, so this is going to be the y values in our unit circle. So our output values up here. All right, so as you notice, let's look. I'm gonna get my highlighters rolling here again. I'm gonna maybe go green, of course, which everyone enjoys. So I'm looking for my y value. So my sine is gonna travel from 0, and then it's going to be increasing, increasing, increasing all the way up to 1. And then it's going to go back again to 0. And then it's going to go way down to -1 and then travel back to 0. All right, so sine's going to look a little bit different, but very similar because as you notice, it still has the same values. They're just occurring at different points in time. All right, so I'm going to set up my structure. Again, we're going freehand here in distance learning. I've got my 0. I'm going all the way out to 2 pi. I'm going to kind of leave degrees out. Who needs it? Pi over 2, 3 pi over 2. All right, there's the structure. And what you guys now know is these are going to be our parent points moving forward. So this one, the largest y value on the unit circle is going to be up here at 1. The smallest y value is going to be down here at -1. So again, for my parent, I'm up 1 and I'm down 1. And now if you think about how this is going to unfold, let's get a pretty x value. So this one is going to start at 0. So there's my point 0. The very next point, or the 30-degree marker, is going to be up there at 1/2. So I'm going to put that point right in there too. Now I'm going to have 0.71. We already have these over here. 0.87. So I'm going 0.71, 0.87, and then I'm up there at 1. So you can see, well, more or less, that's not really that pretty. So as you can see, the rate of change, it's going to change quickly at first, and then it's going to slow down over time. So again, we're going to have this wave motion. And in terms of time, we know that that's going to happen on the other side too. You're going to start up there at 0.87, and then you're going to go to 0.7, and then down here at 0.5. Oh, that was really bad. Sorry, maybe over there. All right, so we know that at pi, halfway around the unit circle, we're back down there at 0. And this is going to follow that slow at first and then quickly over time. Think about those rates of change. Now we know that at 3 pi over 2, we're going to be way down there at -1. And once again, quickly at first and then slowing down. And then slow at first and back up there to 2 pi. And then the same thing occur for period, amplitude, and range. I'm going to make my sticky note real quick. So here's my sticky note for my sine curve. So I've got an input of an angle, an output of a sine. Now you'll notice the patterns are exactly the same. However, cosine starts at 1. This one starts at 0. Sine's my personal favorite. All right, so here we go. If I were just going to sketch this out for my future, I'm going 0 all the way out to 2 pi. Half of that is pi. Half of that is pi over 2. You guys can get so good at this. 1 pi over 2, 2 pi over 2. Yep, 3 pi over 2. Up at 1. Down at 1. Now remember, sine are my y values. So if you forget where this is going to start, think about that unit circle. My y value where the unit circle starts is 0. So this is going to be your start at 0, end at 0. So we start at 0, travel up, travel down. Now we're in the negatives. back to the positive. So my sine curve looks like this. I always say that life is like a sine curve. I'm not even kidding. All right, period. How long does it take this thing to unfold? Yep, 0 to 2 pi. So our period is going to be 2 pi. Amplitude, how tall is this wave? Our vertical height is going to be 1. And our range for this one is going to be from -1 to 1 once again. So you can see sine was a lot quicker. Okay, we're approaching the 30-minute mark here in about 5 minutes, but as I told you, this video will probably go about 45 or so, and then the next video you watch this week should only be about 15 minutes. We're really gonna try to honor that time commitment that you guys have while you're trying to balance all your classes. Whew, a lot going on here on this piece. What I want to do now is I want to show you, of course, if we have parent functions, you can't call anybody a parent until they have babies. So these are, of course, going to produce some transformed functions or some offspring from these parent functions. So what I'm going to do now is I'm going to take these deep notes and I'm going to lose this beautiful notes sheet that I'll say forever. And what I'm going to do now here on page 2 is now I'm going to transform these functions. So I'm going to keep them over here for handy dandy reference. And we are going to look at today some scale changes and reflections. Because of course, transformations work on every function, and that includes trig functions. So remember, scale changes are going to be changing the size vertically or horizontally to stretch something to make it grow twice as fast or 3 times as fast or slower. And then reflections, of course, are going to be vertical reflections or horizontal reflections over the axes. So if we take a look at example 1, and this is kind of what your practice problems are going to be today. We're going to kick it up a notch next time, but this is all the basics. So let's say that we have f of theta, and we've got 3 times the sine of theta. So here's my offspring function. And we are going to restrict the domain. We want to travel from -2 pi, that's right, all the way to 2 pi. So we're traveling a little bit more than one parent function, or one period. We're actually going to end up with 2 periods. So you can see I've got my little sine function here. So this time my sine function is not only going to travel to 2 pi, but I want to see what happens before that. What happens at from -2 pi all the way to 2 pi. All right, so when I look at this function, I can see that the new thing is going to be this 3. All right, well, this 3 is happening outside of my function. So this is going to affect my outputs. And what's going to happen is, because this is a multiplier of 3, instead of going up to 1 and down to 1, what if this is going to be a scale change of 3? So this time, this function is going to have a vertical scale change by a factor of 3. This vertical scale change is going to be changing the amplitude. So this time, I'm going to define my amplitude is going to be 3 because of that vertical multiplier. You could make a table. I find it a lot quicker just to start labeling my graph. Oh, I already messed up. Dang it. Why did I mess up? Well, because I put my axis over here, and we know that I have to travel from -2 pi. Well, that's okay. I'll just make it smaller. See? Happy mistakes. Happy mistakes? What does he say? I forget. Okay, so here we go. I'm going to set up my structure. I'm going to start with this new weird amplitude. Instead of going up to 1 and down to 1, guess what I can do? I can just go up to 3, which means I'm going down to -3. That's right, just that simple. All right, now I need to travel from -2 pi, so that's way back here. Sorry, -2 pi. All the way up to 2 pi. Now, it would be great if your graphs were a little bigger, but remember, I messed up, so oh well, I'm just going to go with it. Okay, so now I'm going to go everyone in between. I prefer, the positives because I'm most familiar with these. Pi over 2, 3 pi over 2. which means in this part of my domain, same thing, except this time I'm in the negatives. So negative pi over 2, negative 3 pi over 2. If I'm going too fast, just pause me. It's your privilege now. Okay, so I'm going to unfold this part of my unit circle first. Nothing has happened inside the function, which means my inputs are not going to change at all. So I've got my little sign cheater here. Starts at 0, ends at 0. So I'm going to start at 0. I'm going to go at pi over 2. Used to go up to 1. Now it's going to be much faster. I'm going to travel all the way to 3. Back to 0. Down to negative 3. Up to 2 pi. So this is just going to be a much faster growing and shrinking function. There's one period. But now I wanted to go back to negative 2 pi, which means, okay, follow that periodic motion. For this one, I'm going to be going down. There we go. As long as you're making your curves, you're good to go. Okay, so something that we're going to need from you, not only the amplitude, but we also need the period. So for the period of this function, remember, we're showing 2 periods, but the amount of time that it takes for one period to unfold is still 2 pi. Amplitude is 3, and my range has changed. F of theta is going to go from negative 3 to 3, because it has been stretched 3 times. Kind of cool. All right, put that up there, and now we're good to go. Okay, let's do another one. I'm going to try to do a twofer on this one. We'll see how that goes. So number 2, let's try h of theta. Let's see if this is going to be negative cosine of 2 theta. And I want this to travel from 0 to 2 pi. Okay. So on this one, you can see that we have a vertical reflection. So right here, this is output, so we're going to have a vertical reflection. And now this is inside the function. So it's going to affect your inputs inversely. So inside inputs inverse, which means if I'm talking about the inside of a function, this is going to be, take a look at this cosine here. This is going to be affecting the period of the function. So here's my inputs. This is not going to happen twice as fast. This is going to happen half as quickly. So on this one, I'm going to change the period. Now, the period used to be 2 pi. And now instead of unfolding in 2 pi, the inverse of multiply is divide. I'm going to divide that by 2. So my new period is going to be pi. So the entire thing is going to unfold in a period of pi. It's going to be unfolding a lot quicker than usual. Okay, so I don't think anything has changed with the amplitude. So I might just say that the amplitude is still 1, which means my range is still going to be 1, or negative 1 to 1. All right, so let's take a look at what this looks like. So here's my cheat sheet. I'm going to make my new, now this time I'm not going to be so silly. I know it's going to start at 0, and I want it to go to 2 pi. Okay, so I can put my axis way over here this time. Honestly, Miss Moore. It's like you're sitting at home watching it snow in your sweatpants. I know. Children are somewhere. I'm sure they're looking at screens. Okay, so let's see. I'm going to start with my amplitude. I'm still using my 1s. So I'm going to go from negative 1 to positive 1. I'm good to go there. The period, this thing is going to unfold in a period of pi, but I need to show 2 periods because I'm going to go all the way to 2 pi. So I'm going to put my pi right here, and I'm going to kind of let it hang out there for a second. So first I'm going to build the building blocks just for one period of this function. Now remember, inside input's inverse, so it's going to unfold in half the time. So if this is where I'm going to end one period, all right, half of that, pi over 2. Now remember, I'm going to build the same way I build these. I go half, and then I go half again. All right, well, what's half of a half? Perfect, a fourth. Now here's where I like my patterns because fractions freak me out. So I'm going to figure out what this one's going to be. 1 pi over 4, 2 pi over 4. There you go, 3 pi over 4. Makes it so much easier. All right, now we know we need to map another period of the function, so I'm going to go all the way out there to 2 pi. Okay, well, I'm going to build the same thing. Half of that is going to be 3 pi over 2. And now you're like, oh man, Miss Moore, but what are these ones going to be? Yeah, I know. Have no fear. Here we go. 3 pi over 4. 4 pi over 4 is pi, which means this one, 5 pi over 4, 6 pi over 4, 7 pi over 4. See? Patterns. Makes everything easier. All right, so let's build our structure now. Now I know it's going to kind of unfold to here. So cosine starts up, ends up. So I'm going from 1 down through pi over 4. No, I'm not. Thank you for stopping me, whoever you are in the front row, back row, side row, your bed, wherever it is you are. I forgot about that vertical reflection. Hello. So instead of starting up at 1, what's really going to happen? That's right. Whoop! So really, this thing's going to start down at 1. Oh my. And end down at 1. All right, so let's just graph this first one. Let's see what that looks like. Yeah, kind of cool. It's like that whole thing was turned on its head. And then the same thing repeats itself. And there we go. Oh, that's pretty sweet. So the period is pi. Amplitude hasn't changed. The whole thing's been turned upside down on its head, but so what? We're good to go. And now you have that sweet cosine wave. I love it. All right, how you guys feeling so far? You feeling good? Strong, my friends? Well, if not, you can go back and watch it again. All right, got my 2 cheat sheets here. Here's sine and cosine. As you know, we still have one more trig function on about 36 minutes. I feel like I'm rocking it. I warned you it'd be a little long on this one, but we'll catch up on the next one. Give you back your time. So we've got cosine, we've got sine, and the last one we need is going to be this tangent piece, which is, of course, the one that we have saved for last because tangent can be incredibly weird. Why can tangent be weird? Why is it going to end up being so weird? That's right. Tangent is going to be so strange because remember, in our unit circle, tangent is going to end up being undefined in some pieces. And what does undefined look like in terms of a function? You heard it right. Asymptote. All right, I need another sheet of paper. Here we go. Okay, so we need to see what's going on with tangent. This is our last one, and then you'll be free. All right, so f of theta, tangent of theta. Theta's going to get crazy. I'm going to stay super organized with my highlighters. Still practicing those good student skills. So tangent, I'm going to look back at my unit circle here for a minute. So I'm going to put my new paper right here so I can use a unit circle that I already had going. So remember, tangent's going to look a little weird because tangent, as we know, is going to be sine over cosine. And you end up with some craziness. You've got to do some rationalizing of denominators and all that kind of stuff. So as I work through the tangents, I'm just going to kind of sketch a little first quadrant. So when I'm here at 0, my tangent at 0 is going to be 0 divided by 1, or so my tangent is actually 0. All right, what happens up here? Yeah, this time I have 1 divided by 0. So my tangent is going to be undefined in these two vertical pieces of my unit circle. So I've got zeros and I have undefines. All right, those will be the building blocks of my tangent function. Okay, well, we need something besides zeros and undefines. So let's think about some other important tangent. Everybody loves tangent of our fourths or tangent of our 45s because root 2 divided by root 2 is 1. So tangent's going to be positive 1 here. Tangent is going to be positive 1 here. And then we're going to have positive divided by a negative. So I'm going to have tangent a negative 1 and tangent a negative 1. All right, pretty cool. I'm going to leave it like that for now, and we're going to fill in the rest of the building blocks in a minute. So here I go with my tangent function. All right, so Tangent's pretty crazy because of these undefines. So for right now, I'm going to kind of put my 0 axis over here. Here's going to be my big axis. And I'm going to start with my 0. I'm going to go all the way out to 2 pi. And then there's my pi. And then there's my pi over 2. And my 3 pi over 2. All right, let's see what's going on here. So with tangent, tangent's a little weird because I don't start with an axis. I start with my undefines. So when you think about something that's undefined, we've done this before, undefined is going to create this building block, this awesome and most powerful asymptote. So I'm going to end up with an asymptote all the way through pi over 2. So at pi over 2, my tangent is going to be undefined. Okay, it's also going to be undefined at 3 pi over 2, which is kind of cool. And then I've got my 0. So I've got my 1s and my negative 1s. All right, so here's my undefines. I've already handled those. Here's my asymptotes. All right, well, what's going on at my 0s? At 0, my tangent is 0. Awesome. And at pi, my tangent is 0. Okay, if we keep going around, it's going to be 0 again. So there's that periodic motion repeating itself. All right, let's put in some more building blocks. What about at pi over 4? So at pi over 4, the tangent is going to be up here at 1. At 3 pi over 4, the tangent is going to be down here at negative 1. 5 pi over 4, tangent's going to be back up here at 1. So you can see this pattern, 1s and negative 1s. Kind of awesome. As we travel through, we know tangents, what time is it? 41, I'm doing good. All right, tangent at my 30 degrees is going to be that root 3 over 3. Okay, well, root 3 over 3 is approximately 0.58. So root 3 over 3, 0.58, that's going to be like right there-ish, which means it's also right there-ish. All right, let's do another one. What about, there's my blue. Up here at my 60s, it's root 3. Well, root 3 is approximately 1.73. Okay, wait a minute. So at my 60s, I'm way up here, which makes sense, you know, because I'm traveling towards my asymptote, which means I'm way up here, which means here I'm way down here. Okay, whoa, what's going on here with this crazy curve? So if you look in the middle, what is going to happen is I end up with this 0, negative 1 to 1. This is going to be curving up towards my asymptote. And now check out the concavity. It's going to be curving down towards my asymptote. And there is one branch of your tangent function, which means periodic motion, I'm going to start at 0 here. So this is traveling slowly and then quicker and quicker and quicker. Same thing's going to happen on the other side of 0, slowly at first and then quicker and quicker and quicker. Wait, as it approaches, this one's pi over 2, which means this one's going to approach negative pi over 2. And this process just repeats itself, repeats itself, repeats itself, repeats itself. So tangent's a little bit weird. As I get to my time limit here, tangent's a little bit weird. These branches of tangent continue on and on and on. And if you've ever tried to graph a tangent function in your graphing calculator or in Desmos, you know that tangent does look a little odd. So what we are going to do for the parent function, you know, mathematicians, we love to see what's going on around the origin. So you could technically choose any branch of tangent that you wanted, but we as that is a funky looking branch, man, look at that. Sorry. We as mathematicians like to see what's going on with 0. So we are going to count this as our parent function for tangent. So here we go. Tangent is going to look a little different. F of theta equals tangent of theta. All right, so when I set up my axis, here we go. This time, my 0 is going to go right down the middle. So I've got 0 radians. We know that my building blocks are going to be my asymptotes this time. So I'm going out to pi over 2 and back to negative pi over 2. So I can, you know, I love to use highlighters for my asymptotes. Now my other building blocks, you could use the 0.58s and you can use the 1.73s, but those are quite cumbersome. So we're still just going to use our 1 and our negative 1. And half of a half, we're going to use that pi over 4 because tangent at pi over 4 is 1. And tangent at negative pi over 4 is negative 1. Tangent of 0 is 0. So here are the building blocks. And as long as you keep those rates of change good, so slower at first, quicker over time as we approach the asymptote, and then the same thing over here, we're good to go. So on this one, period for my parent function for tangent, one period of tangent unfolds in a distance of pi. If I'm going from negative pi over 2, that's half a pi, and there's another half of pi. So the period is just going to be pi for the parent function. Amplitude, what is the height of this wave? Well, there is no wave. The height is infinite. So we are not going to have an amplitude. And as you can see, our range is going to travel from negative infinity. I guess we can still do range. We're going from negative infinity all the way up to positive infinity, not inclusive. Oh, 46 minutes. All right, I'll get you quicker on the next one. Thank you for hanging in here on this long video. I apologize if you got tired or fell asleep. It's here for you whenever it is you'd need it. I just want you to know that it is still snowing here on April 27th. You have a worksheet assignment that is attached to plan book, and it is a series of, I think we're asking you to do 5 problems. 2 problems are extensions. Good luck. Answer key is pretty good. See you at the Zoom.